Hello, welcome back to another video lecture. Today we're talking about section 2.5, limits at infinity. As a brief review, hopefully you watched the video entitled section 2.4, which was about vertical asymptotes. A vertical asymptote, to kind of give us some visualization here, a vertical asymptote is one where our function, let's say, shoots down towards infinity across a, maybe an impossible threshold. And then later on, maybe it comes back. We call this dashed line right here, we call that a vertical asymptote, in that it's a vertical line that the graph seems to asymptotically follow. And the word asymptote also has the same root as the word symptom. Where it's a symptom that the graph possesses. It's just like a fact about the graph. Instead, we want to talk about horizontal asymptotes. So notice, a vertical asymptote, there's a finite x value, but infinite vertical y values. A horizontal asymptote is different. As we let x values grow infinitely, i.e., we take a limit as x approaches infinity, maybe we can calculate some finite y value. And once again, the reason y limits, there's no such thing as f of 100. Sorry, f of 1,000. I keep reading them as zeros. There's no such thing as f of infinity. And again, what do we do when we are interested in a value that is unevaluatable? We instead take the limit. Okay, so a couple of things just to kind of get us on the same page. A set of functions that they explicitly will not have any vertical asymptotes or horizontal asymptotes. And the type of function that is something called a polynomial, where it's real basic, 3x squared plus 4x minus 9, your cubics, your quartics, your degrees 5, all of those, they don't have vertical asymptotes, they don't have horizontal asymptotes. Okay? Now, there are some functions that can have horizontal asymptotes, but they do not have vertical asymptotes. And right now, that's going to be our exponential type looking function. So here's an example of a function that has a horizontal asymptote, and we'll talk about finding it. The last one, and this is the one we're going to spend the most time with, functions that can have both horizontal asymptotes and vertical asymptotes. And those are going to be rational functions. Rational, coming from the same root word under ratio, it is a division of two functions, specifically two polynomials. Okay? Now, if you make something outside of this group, it could have some interesting behavior, but right now those are the behaviors we want to talk about. And we're going to talk about each of them differently, and we're going to have some rules about each. So I'm actually going to zoom us out, and we're going to start right back over here. And I want to talk about what our first type is. So I want to talk about doing some rational type horizontal asymptotes. Now, these could also have vertical asymptotes. We're not going to talk about those until later, but right now we're going to focusing on these horizontal asymptotes. So this is the important rule, and I'm going to write this in a different color because I really want it to stand out. Hopefully this purple, royal purple, stands out a little bit. Here is a very few times in this class do I get to write down a law. This is something that is always true. The limit as x approaches infinity of 1 divided by x to the p equals 0 if p is a positive number. Okay? Now, similarly, I do have to amend it slightly when we're talking about the negative root But you know what? I'm actually not going to do that. I'm going to say, as long as p is greater than 0, you're going to get these behaviors. As long as p are these whole number integers greater than 0, you are confident that the limit is going to equal 0. So we're going to combine that with a couple of our other limit properties, see what we can find. So what about something like this? What is the limit as x approaches infinity of 3x to the negative 9? Note, we cannot plug in infinity. That's why we're talking about the limit. So we need to treat this as limits, and we're going to use the rules on limits to try to get by. So reminder, we can pull out constants. 3 times the limit as x approaches infinity of x to the negative 9. We're going to rewrite 3 times the limit as x approaches infinity of 1 over x to the 9. And 9 bigger than 0, this is going to be 3 times 0 is 0. And there's our answer. The limit as x approaches infinity of 3 times x to the negative 9 equals 0. Notice, it wasn't until this step right here did I actually end up using either of these things. So we're going to pull out the constants, we're going to move those around. Now, this setup is easy. I mean, it seems obvious. As long as we can write something like 1 over x to some power, and as long as that power is positive, we'll be able to identify these horizontal asymptotes. Let's go something maybe a little bit trickier. Let's go example 2. Let's do the limit as x approaches negative infinity of 3x to the negative 9 plus 4x to the negative 2 minus 1 over x. Okay? We're going to use a different rule here, and specifically we can distribute over plus and minus. We can actually split this into 1, 2, 3 different limits, and they all have the same behavior in that they're all going to negative infinity. So it's going to be 3x to the negative 9 plus the limit as x approaches negative infinity of 4x to the negative 2 minus the limit as x approaches negative infinity of 1 over x. Now, once we're here, we can start treating these exactly the same way. And again, we can pull out a constant, we can pull out a constant, and rewrite. This is 3 times the limit as x approaches negative infinity of 1 over x to the 9 plus 4 times the limit as x approaches negative infinity of 1 over x squared minus the limit as x approaches negative infinity of 1 over x. And for each of these, and maybe I should specify, this is x to the power 1. P bigger than 0, p bigger than 0, p bigger than 0, 0 plus 0 plus 0, still 0. So right now it seems like a lot of these limits are 0. Let's talk about one that's not going to be 0. This is going to be a more interesting rational function. So let's take a look at the limit as x approaches infinity of, let's come up with an interesting rational function, just kind of choosing one off the top of my head. Now, the important thing here is there's no amount of distribution that I really want to do that's going to make this any easier. That's going to be not good. So instead, I have to think about what I can do. And the most important thing that I can do is I can always simplify x over x in a limit. That's the first thing I want you to recognize. We can always simplify x over x in a limit. And the second thing is that I like 1 over x to the p. That's what I like. So the question is, how are we going to combine those two ideas? So the most important thing that we're going to be able to do, let me write this in a different color once again. Number 1. In this case, find the largest value of x that appears and divide it out. That's going to be our guiding principle. So, what is the largest value of x that I see? And by the largest value, I mean largest power of x that appears. And I think that happens right at this term right here. We have this x squared term. So, both top and bottom, I'm going to divide out. I'm just going to do a rewrite where I'm going to distribute or sort of undistribute that out. So I've taken away an x squared. So what will that leave in the first place? Well, 4 taking out an x squared. Well, we took away a x squared from 4, which means that we divided it by x squared. So we got 4 over x squared minus 3. There already was an x there, but we took 2, which means there's going to be a 1 on top, or sorry, a 1x on the bottom, and then there's going to be a 7. We're going to do that both top and bottom. Okay? Now when we take away it here, reminder, on that 3x, we're going to get 3 over x plus 1 over x squared. Now, reminder, we can always simplify x divided by x in a limit, and so we're just going to do that twice. This term, x squared, again, how do I know that x is not 0? Because I'm in a limit. And not only am I in a limit, I'm in a limit as x approaches infinity. So x is actually, I have some assurance that it's quite large. So, what this limit becomes is the limit as x approaches infinity of 4 over x squared minus 3x plus 7 divided by 3x plus 1 over x squared. Let's rewrite that. The limit as x approaches infinity of 4 over x squared minus 3x plus 7 divided by 3 over x plus 1 over x squared. Now, we can start tackling this issue on its own. Now, once that we've written it like things that I like, now we're going to distribute this limit, and we're going to distribute it top and bottom. So this is going to be the limit as x approaches infinity of 4 over x squared. And as you guys have seen, that's going to equal 0. Minus 3 over x, whoops, forgot my limit, of 3 over x. And a reminder, that's going to go to 0. Now, plus the limit as x approaches infinity of the term 7. And as it turns out, that's not 0. It turns out it's actually going to be 7. Now, what's happening on the bottom? We have the limit as x approaches infinity of 3 over x. As a reminder, that's 0, plus the limit as x goes to infinity of 1 over x squared. And as a reminder, that's also going to 0. Now, we have something bad. In that, 0 plus 0 equals 0, which tells me that this limit right here, because I'm dividing by 0, is not finite. That's the important part. It's not finite. It is going to be an infinite limit, right? The horizontal asymptote, as you go across, is going itself to be heading towards infinity. Now, what that actually tells me, though, is that I can get a boundary on it. I can kind of know what it's going to be like if I just plug in a fairly large value of x. As a reminder, this is the limit as x is approaching infinity. Let's try, and we're really just trying to get a sign. Let's try f of 1,000. That's something that we can plug in. So I'm going to go back to the original, take what's ever in there. I'm going to say 4 minus 3 times 1,000 plus 7 times 1,000 divided by 3 times 1,000 plus 1. And the central idea is compare 1,000 squared is much larger than 1,000. So this term and this term don't really do anything. And the whole point is that this term dominates. And this term is itself positive. Therefore, the limit as x approaches infinity is not finite, but the limit is positive infinity. Now, this test that I have where I pull out the largest power of x that appears, it's really, really good at finding finite limits, if they exist. But it will tell me when there aren't any. And you might have learned in your pre-calculus course, you might have learned, oh, there's a certain relationship between powers on top and powers on bottom. That's absolutely fine. I'm not going to say that that's not true. I am going to say that it is going to grow without boundary. So let's try to find a rational limit of this type that maybe does have a finite. Let's try to see it where it actually ends up working. Okay? Let's try something like this. What is the limit as x approaches infinity of 2 plus 4x minus 8x cubed divided by x to the 5? So, once again, pull out, or I shouldn't say pull out, divide by highest power. This is going to be the limit as x approaches infinity of, well, what's the highest power? I see it as this x to the 5th that appears in the denominator, so I'm going to divide top and bottom by x to the 5. This is going to be x to the 5 times 2 over x to the 5 plus 4 over x to the 4 minus 8 over x squared divided by x to the 5. What am I going to be left with? Just 1. So, pulling that out, and again, why do I pull out that power of x? Because I know in a limit I can cancel these terms. And now I'm going to spread it out. Both top and bottom. This is going to be, it's a lot to write. 2 over x to the 5 plus the limit as x approaches infinity of 4 over x to the 4. Grab myself some more room. Minus the limit as x approaches infinity, 8x squared, divided by the limit as x approaches infinity of 1. So, as x gets larger and larger and larger, this denominator term becomes larger and larger and larger. This term goes to 0. As x gets larger and larger and larger, the denominator gets larger and larger. This term goes to 0. And as x goes larger and larger and larger, the denominator gets larger and larger and larger. This term goes to 0. So we have 0 on top. That's not an issue. The issue is if we have 0 on the bottom. But as x gets larger and larger and larger, it just stays 1. So 0 plus 0 minus 0 over 1, that's a finite value of 0. And that actually goes back and it answers the question, the limit as x approaches infinity of 2 plus 4x minus 8x cubed divided by x to the 5th is 0. And again, this might be a pre-calculus rule where you say, oh, the degree is larger on the bottom than it is the top. We're done with those rules. We want something algebraic. We want something that we know works. And right now, this is what we want. I'll leave the case when it comes out to be a constant for yourself. That's something you'll discover in the homework. Okay, something else that we want to talk about is what happens to some of these more interesting pieces of rational functions. Can we always do this trick? And so one of the tricks I want to take a look at is what happens if we take a look at the limit as x approaches, negative infinity of something like the square root of 441x squared plus x divided by x. That's the question that we want to answer. Can we still do that thing where we divide out our most highest power? And in an effect, we can. Notice, however, that if we do this, we have to realize that the highest power is a little bit more complicated. Highest power. Okay? I would say that the highest power is either this term or this term. Notice the term on top is something the square root of x squared, and the something on bottom is just x to the 1. It turns out these two things are, I'm not going to say the same, but these things are almost the same. In fact, there's really only one big difference. It has to do with the sign. It has to do with the sign. This term is always positive. This term can be either. So, we do want to divide out by this highest power, but what that highest power is going to be different top and bottom. So this is going to be rewrite as the x approaches negative infinity. Actually, I need a larger box because this one starts to get pretty big. So here's my big subtraction symbol. On the bottom, we're going to have x divided by x. But on top, we're going to have the square root of 441x squared plus x. And we're going to divide that whole thing by negative the square root of x squared. Why negative? It's because we're taking a limit as x approaches negative infinity, and we don't want to lock ourselves. We have to choose this thing being always positive. We have to sort of make it be negative in order to satisfy this. If this negative sign weren't here, we wouldn't be doing that specific one. Okay? Now, can we simplify this at all? And the answer is, of course, x approaches negative infinity. That's why we do it. So dividing, because both of these are underneath a square root, we can combine them. This is going to be the square root. I'm sorry, I forgot a 1 when I wrote that. This is going to be the square root, the negative square root of 441 plus 1 over x divided by 1. Okay? Now we're going to bring it in. And we can actually bring the limit inside the radical. This is going to be negative the square root of the limit as x approaches negative infinity of 441 plus the limit as x approaches negative infinity of 1 over x. And hopefully this is something that we both know. Specifically, This is a constant, and it's unaffected by the limit, so it's going to stay. And this one is a power, goes to 0. So our answer, what is the negative square root of 441? I'll be honest, off the top of my head, I don't remember that. This is why we go to our calculators. We find what is the square root of 441. And reminder, we want the negative of this. My calculator is telling it that it is negative 21. Now, it is true that if you have access to some sort of graphing calculator, a lot of these horizontal asymptotes become a lot simpler. For example, if we actually plug this one in directly, it's going to be the square root of 441x squared plus x divided by x. Once you start to take a look to the right, you can see this thing is heading towards 21 to the right, but negative 21, our answer, to the left. It doesn't actually take that far. If you really zoom out in a macro sense, not 1,000. Let's go out maybe 10,000. It just straight up tells us the answer is 21. So again, I would prefer if you were using a lot of these, algebraic techniques to find these. But as a reminder, you can almost always check yourself with a graph. Now, here's the important part. This process that I've done right here, this process, where we're dividing out these highest powers and showing me that process, that's what this course is. Don't become too reliant on checking yourself. We want to make sure that checking ourselves is done after we've tried something, because ultimately you won't have the ability to check yourself that well on something like an exam. Okay, so I think that's good for rational type functions. Let's talk about another type of function that has the potential. We have the concept of the exponential function. Now, the exponential function is kind of interesting in that if I graph something like y equals e to the x, it looks like this. And so notice, the only part, the left side, behaves like a horizontal asymptote only. The limit as x approaches negative infinity of e to the x is 0. But the limit as x approaches positive infinity of e to the x, well, that's going to grow without bound to infinity. So, exponential functions, only one side has a horizontal asymptote. And that's an interesting behavior. Notice, whatever I said in the rational function, what was ever true for the negative or the positive, in this case, if I go back to the previous example, if I had switched this negative infinity with a positive infinity, the end result is that it would just cause the last one to be positive. Okay? And if I go back to this one, because it's 0, I'll point out, it was 0 either direction. It's only on exponential type functions that we're going to see this behavior where, one side is going to have a horizontal asymptote and the other one is going to grow pretty much without bound. And maybe it grows in a positive direction, maybe it grows in a negative direction. But ultimately, that sidedness makes exponential functions a little bit trickier. So, what if we start playing around with some exponential type functions? What if we have something like 16e to the negative x plus 4? And we'll take a look at the limit as x approaches infinity of that. Well, once again, we like this idea of distributing out our limit sign. can pull out a constant, 16, the limit as x approaches infinity of e to the negative x, plus the limit as x approaches infinity of 4. Now, this term, that term equals 4. Because, again, notice 4 doesn't depend on x. What about this one? X is going towards infinity, but this is e to the negative x. I want to do a real quick change of variable. And this is just one way. This is not the way that your book tries to associate this answer, but it is the way that I like to do it because I think it's a little bit faster. We're going to do a change of variables. I want to switch negative x to be positive t. It's going to be 16 times the limit. So, as x approaches infinity, is going to imply that t is going to approach negative infinity. This is the limit as t approaches negative infinity of e to the t. Reminder, plus 4. And this one is that left side. So I always like to write whatever's inside. I always like to turn that into e to the x. So I can compare it to these two rules. So what is the limit as t approaches negative infinity of e to the t? This term is 0. And our answer is 4. So, a change of variables is kind of quick. It's simple enough as long as you remind yourselves. And I always like to turn whatever's inside the limit back into e to the x, just so that I can always compare it to here. And even if you have something like, let's say, just as an example, unfortunately I'm just trying to come up with one. What if we say something like, oh, what is the limit as x approaches infinity of e to the negative 14x? Well, once again, I'm going to do a change of variables. Negative 14x is going to go to t. So as x grows more positive, t is going to grow more negative. So I can rewrite this as the limit as t approaches negative infinity of e to the t, once again, equaling 0. Now, not all exponential limits equal, it's just the two examples that I chose. And maybe I should have chosen a third example, but you'll get lots of examples in the homework. Okay, the last one that I want to talk about is I want to talk about a function that we have largely ignored, which is the logarithm. And this is a really counterintuitive fact. But this is sort of what the base logarithm looks like. Also, this pin color is very cool. It looks like this. A logarithm typically has a vertical asymptote, but no horizontal asymptote. And by that I mean it seems impossible. It seems like this sort of behavior is dying off. But it's really not. It really is becoming larger and larger and larger. So the limit as x approaches infinity of, let's just say, the log base 32 of x, that actually grows without bound. It actually will grow forever, which seems counterintuitive. Now, the limit as x approaches negative infinity, you got to be real careful with these logarithms. Because log base 32 of negative 1, or any negative number, not allowed. We got to restrict a lot of these logarithms from having negative values. So that's a little more interesting. Now, this vertical asymptote, once again, notice it is the limit as x approaches zero only from the right. Because there's nothing over here. It's outside of the domain. Reminder, the logarithm has a domain typically from from 0 to positive infinity. Now, if you switch this around, if you do something like, oh, what about the log of 2x minus 1? Well, that has a domain of, I believe, 1/2 to infinity. So again, there's ways around this. There's ways to make this different, but ultimately, we would expect only right-sided limits. Now, with reflections and translations, this gets a little difficult. Reminder, you always have the ability to graph, but again, that graphing should be in support of an algebraic argument that you've made. So let's take a look at a random homework question that I'm just taking a look at. This looks like question number... on your homework, it looks like question number 21. So, hopefully this helps. Consider f of x equals, we'll go out. So this is 2x cubed plus 14x squared plus 20x divided by x cubed plus 5x squared. And it wants to find the limit as x approaches infinity and the limit as x approaches negative infinity. Okay, so we know exactly how to find these things of f of x. As a reminder, we're going to divide out by the highest power. What's the highest power? I think it's this x cubed term. So this is going to be the limit as x approaches infinity. Take out that x cubed. What are we left with? 2 plus 14 over x plus 20 over x squared. Divided by another x cubed. 1 plus 5 over x. All right. Once again, we can cancel those terms, leaving us, getting a phone call, distributing out this limit to the numerator and the denominator. The limit as x approaches infinity of 2 plus the limit as x approaches infinity of 14 over x plus the limit as x approaches infinity of 20 over x squared, all divided by the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 5 over x. And remember our rule. Constant, this term is 2. Something over a power of x, gone. This term is 0. Something over a power of x, gone. This term is 0. Constant, 1. Power over x, 0. What do we get? 2 over 1, where the answer is 2. Now, as it turns out, everything that I just said for the positive infinity, if you literally, let me kind of zoom out here, I'm going to try this. It didn't work. I just want to make a selection. Will it really not let me do that? Let me copy that. Ha-ha! I'm getting a little bit better. Notice, if I change each of these to be negative infinity, everything is the exact same. Just for this specific one. That's not true in general, but it turns out most of the time in pure polynomial rational type answers, you're only ever considering, most of the time they share. It's really the exponentials, the logarithms, those things usually have different ones. Now this question continues and it asks, where are the, so what is the what is the horizontal asymptote? And I will point out, because these two things are the same, that is what we call the equation of a horizontal asymptote. Now, it's the entire equation y equals 2. Don't just type in 2. Horizontal asymptotes are equations of y. Vertical asymptotes are equations of x. And we'll hopefully get to that one on the third part. So now we want to talk about a vertical asymptote. So notice a vertical asymptote. This is our original function, f. Let's rewrite that. Let's go vertical asymptotes. Reminder, f of x is 2x cubed plus 14x squared plus 20x divided by x cubed plus 5x squared. Now the first thing that we want to do when we're talking about vertical asymptotes is we want to make sure that we factor. Now the top can be factored a lot, but as it turns out, mainly what we're going to do is we're going to pull out a 2x, leaving us with x squared plus 7x plus 5. And on the bottom, we're going to pull out an x squared over x plus 5. Now, if you really take a look at this equation, we have to ask ourselves, what are the factors of 5? 1 and 5, do those add up to 7? The answer is no. Oh, goodness. I apologize. I just want to hit undo. It's making me live with my mistake, which I don't want to do. It should be plus 10. And the factors are 2 and 5, which turn out to be, yes, these actually do factor quite nicely. We can actually factor even further as x plus 5 and x plus 2. And the reason that's important is if we take a look at our denominator, x squared times x plus 5, our candidates for vertical asymptotes are x equals 0 and x equals negative 5. And the vertical asymptote is going to appear at x equals 0, but not x equals negative 5. Why? Well, this negative x plus 5 cancels with this x plus 5 in the limit, but there are 2 x zeros and only 1 here, meaning one of these would cancel with one of these, and notice we're still left with an x in the denominator. So there's only one asymptote, which is x equals 0. But the question is, what values do we get as we start to plug them in? So what is the, for example, limit as x approaches 0 from the right? So this is going to be the limit of 2x times x plus 5 times x plus 2 over x squared times x plus 5. Now, as a reminder, we can cancel that out, we can cancel one of those, we can cancel this whole term out, we can cancel one of those. And so x, as it approaches 0 from the right, x is bigger than 0. This is going to be the limit as x approaches 0 to positive times x plus 2. Well, x is bigger than 0. This is also going to be positive. Divided by x, which is also going to be positive. And the end result is a positive number times a positive number times a positive number. We're going to get positive infinity as it approaches from the right. Just plugging this in. Now, what happens as we plug in from the left? Well, pretty much the same thing. However, ever so slightly importantly, keep in mind that now x is going to be less than 0. Okay? So the limit coming down here, as x approaches 0 from the left, remember, x is less than 0. We'll go ahead and do our cancellation, x plus 2, x. So as a reminder, 2, always positive. Now, x is less than 0, but it's close. So if we add 2, we'll still get a positive number. But the important thing is that this number is negative, meaning our answer will be negative infinity. And just to kind of prove that being done, I answered this homework question, which is what I was just trying to do right now. And here are all of the parts. And hopefully I explained each of those parts. So if you would like some homework help, I'd be more than happy to help you one-on-one, asynchronously. I can record more videos. Several of you have used the Ask My Instructor. So let me just shout that out again. If you look at the bottom of your assignment, you can help me solve this, view an example. Those are all well and good. But you go to this go to this Ask My Instructor. That will send me an email. And I can either, get a digital picture. I think I took a physical picture because I was at my house when somebody asked me a question. So again, whatever you need, please let me know. And hopefully you are all well on your way to being finished with Chapter 2. I think we only have one more section of Chapter 2. And as a reminder, there are 2 quizzes that you want to take a look at at the end of Chapter 2 that's going to be important. So have a wonderful rest of your days, and I will see you all in the next video. Although I won't see you. And you won't see me, because I'm not showing my camera. Send me an email if you want to know what I look like. I'll give you a hint. I am somewhere on this page.